Okay, we started with back propagation. We got to know the definition of back propagation. What is back propagation?
Adding some delta to the node. I mean, having initial delta.
So it is finding delta to the every neuron. So it is a way to learn the weights. So how are we going to learn? We are going to learn the delta. So there are two steps for it. So one is learning the delta, and the second step is updating the weights. One is finding delta, and the second, this is called as a back propagation step, and this is called as an update step. Updating the weights for all the neuron is called as update step. So we saw the two types of two steps in the back propagation. So in today's class, we will continue with this. So one more assumption which we made is that there is no activation functions for now. So this is the assumption which we are making. So now we will move on with the same concepts. So we have two key observations. So we are going to learn two key observations. The first observation is that both observations are coming with the assumption that the network is ignoring the activation function. So both the assumptions are using this. Sorry, both the observations are using this assumption. So the first observation is, I'll write down the first observation. So this is the first observation. When any neuron output in the network changes, the output error changes by the proportional amount. So neuron output and output error are related with by a small amount by a proportional amount. So we can say that the output is proportional to the error. So neuron output is proportional to the error. How much it is proportional and all those things we will see now. So for time being, we are ignoring the activation weights. We are concerned about two things. We are concerned about the weights and the neuron outputs. But we are ignoring the activation functions for now. Later on, we will see how to include activation function and then see the values. For now, we are ignoring the activation functions. We are just concerned about the weights and the neuron output. The first observation is that neuron output is proportional to the output error, or else we will say neuron output changes proportionally to the output error. So let's take one small example. So here, if you look at it, except for the first layer neurons, all other neurons, they get the input value from the previous neuron. So they get the input value from the previous neuron. Here, if you look at this layer, they get the input from the previous neuron. So they get the previous layer times the weight in the edge that will come as an input to the current neuron. For every layer except the first layer of neurons, the input values are each of the output of the previous times the weight of the connection which it travels on. So each output is just a sum of all these weighted inputs. So here is an example. So in this example, we have got 4 layers of, so we have got 4 layers. So 4 layers of neurons. The data is flowing from left to right. So if you look at each neuron input, it comes from the output of the neuron on the previous layer. So if you are assuming that your inputs are not going to change, then how the output will change? Only by changing the weights in every layer, the output will change, provided the inputs are going to remain stable. The only way output can change from time to time is by changing these weights. So to find the change in error, what we are going to do is that we need to find the change in neurons output, because we learned that by changing the weights, we can change the output. So how do we find is that the only way we can change the output is by changing these weights. So in other words, to find the change in error, we need to find the change in neuron output and multiply that by a small particular value. So suppose if the change in output is doubled, the change in error also will be doubled. Suppose if the change in output is reduced by half, the change in error will also reduce by half. So you can see the connection between the change in output and the change in error. So the connection between the change in the neuron's output and the resulting change in the final error is just some neuron change times some number. So that number is nothing but delta. So in mathematics, mathematicians usually call delta to be a sum change. So whenever there is a change, they introduce a term called delta. So it's a natural choice to pick for this name. So how it is related means the neuron has this delta value can be positive value or negative value. It can be a small number or it can be a big number. It can be anything. So how this is related is that the neurons, the change in neurons output multiplied by neuron delta will tell you what is your change in the network error. So this is the relationship you need to understand. So the first observation here, what we learned, we said that any neuron output, any change in the neuron output will produce a change in the output error by a proportional amount. So that proportional amount is nothing but the delta, neurons delta. So change in output neuron multiplied by the neuron delta will give you the change in the network error. So let's take one example here. By a brute force method, let's introduce some change in the output.
Madam,
Then
when you say brute force, what is it? Is it a technical term or it's just a raw?
It's an English term. Brute force means
Okay,
I am deliberately introducing what to say,
okay,
a change.
okay, okay.
We need to improve our English.
Oh. Okay. So Let's draw a network and we will understand from that network.
I'm not able to hear.
No, I didn't speak yet. So can you hear me
Okay,
now?
okay. Yeah.
So here you have a neuron D. So for this neuron, you have got three inputs from the previous. You have inputs from three previous neuron A, B, C. So the corresponding weights for this one can be AD, BD, CD are the weights which is lying on these neuron on these edges. So from these three neurons get multiplied with the output from three neurons get multiplied with these weights and then they get added up. And this is your output of D before getting it. So by brute force method, what we are going to do, we are going to add a small change to this output M. So previously our output of D was A into AD plus B into BD plus C into CD. So this was your previous output. So now after this, what happens? The present output of D is M plus your previous output. So the change in output is present output, the difference between the present output and the previous output.
Oh, what is this M, ma'am?
So M is a small change you are adding to it.
Okay.
So that's what I told. By you are deliberately adding some arbitrary number to the summed input just before the value emerges from the neuron's output.
Okay.
So this is M is a modification which you are making to the output of D.
Okay.
Is it clear? So usually that's what I'm saying. Usually, if you consider this as a neuron, it is getting input from three different neurons. So the sum of weighted thing from the previous input will be your current output. So now what you are doing, in addition to your previous output, you are adding a small number to the previous output, that is M. So that is your present output. So what is the change? This was your previous output, this is your present output. So the change is the difference between the two outputs is the change in the output. So the change in the output is nothing but the difference between the present output and the previous output. So the difference between the present output and the previous output is M. So the change in output is M. So for this change in output, so what we saw here, change in output into neurons delta is nothing but your change in neurons output into neuron delta will give you the change in the network error. So this M is the change in output. So this M is multiplied with the delta. So M into delta will give you the change in the error due to M. change in the error due to change in the output. Is it clear? So
Sorry, ma'am. What is delta again?
one second. Yeah. So delta is the number which we discussed here. Did you remember this part which we discussed? So we
Changing.
had the first key observation, no?
Yes.
So the first observation tells us that the change in the neuron output is proportional to the output error. We discussed that if output doubles, error also doubles. If output reduces by 1/2, error also reduces by 1/2.
Ma'am.
So there is a connection between the change in the output and the change in the error. So what is that connection? It is connected by a small number called delta. So every neuron has a number called delta. So how is the relationship between the change in error to the change in network is change in neuron output multiplied by the neuron delta will give you the change in the network error. So that we are seeing, that we saw it as a formula. Now we are seeing it in a pictorial form. So in the pictorial form, so this m is multiplied with the delta. The change in output is multiplied with the delta to give the change in error due to m. So change in error is nothing but m into delta. So the value of m is inside the neuron. So we can also change it in a other form. So it is not necessary always it has to be inside the neuron D. So we can represent it, the change in output can be brought from one of the inputs also. The output, the change in output can be brought by changing one of the inputs. So we can see how it can be done. So previously we saw here that the arbitrary number was added after we got the output. It was added to the previous output. So we changed the previous output by adding some number to it. So then we got the change in output. So the change in output can be brought by changing one of the inputs also. Here B is one of the input. So what I'm doing is that after B gets multiplied with BD, I am adding a number to the input. So here how it becomes. So the output of D is A into AD. So we are adding A plus A into AD plus this term plus this term. So A into AD plus B into BD. B into BD is added with M plus C into CD. So if you look at here, B into BD gets added up with this one, and this is getting added up with this. So if you rearrange this, plus M. So this is nothing but your previous output plus M. So that is your present output. So the change in output again remains as M. Present output, the difference between the present output and the previous output is your change in output, that is M. and that is again multiplied with the delta to find the change in error.
So, ma'am, no doubt, you tend to say that this output can be altered either at the output level and both at the input level itself. By
Yeah, we
adding
can
m at
either,
input stage as well as at the output stage.
yeah, you can bring the change in output. The change in output can be brought out by adding a number at the output stage or by changing one of the inputs.
Yeah, got it.
In either way, you can get the change in output. So how the output will be changed? You need to change the output, or you have to change one of the inputs so that outputs will be changed. That is what we are trying to say here. So the change of the value that's coming is from neuron B. And we know that the output of B will get multiplied by the weight BD before it is used by neuron D. So we are adding a weight right away, and this weight is applied before it is getting added with the M. So if you look at this, the result is just same as the before. We are just adding M to the overall sum that is emerging from the D. So the output of D is again changed by M, and the change in the error is again M times the neuron value of delta. So that is not changed. So this is again M into delta times is nothing but the change in error. So just to recap, the change in neuron output, if you know the change in neuron output, that is if you know M, and if you know the delta value, we can predict the change in error. So how we know? We can multiply the change in output with the delta to get the change in error. So this is a remarkable observation. So if you look at it, how the error changes based, we will know how the error is changing based on the change in the output. So this is related with the change in output. So this delta is acting like an amplifier. Suppose if it has a bigger value, this delta will amplify it much more bigger. If it has a smaller value, it can even make it much more smaller. So this delta is acting like an amplifier for the neurons output to get a bigger or a smaller effect of the network's error. So we can get interesting results by multiplying the neurons change in the output with its delta value. So if the change in the output and the delta value has same sign, if both has the same sign, then the error will be positive. If the error is positive, then the error will increase. So suppose the change in output value and delta value or opposite sign, then the error will have a negative sign and the error will decrease. This one, maybe to be more intuitive, we can explain it with some numbers. For instance, let us assume you have a neuron A. If del is equal to 2 and the output changes by for -2. Let us say that initially the output was 5, now it has come to 3. So the change in output is -2. So here the delta value is positive. Change in output is negative. So if they are in opposite sign, so the error will be negative. So change in output into delta is change in error. So change in output is -2 into plus 2 delta, that is equal to -4. So the error will drop by 4. Let's take another example. Let the delta be -2 this time. Output changes. This time we will say from 3 to 5. So change in output is +2. So change in output into change in error, that is +2 into delta is equal to -4. So this time also the error will reduce by 4. Let's take one more example. This time we will keep delta is equal to -2. Change in output is also -2. So both are same sign. If both are same sign, then we will have a positive error. So the error will increase by 4. So is it clear how the relationship is there? So now this is leading to a second key observation. Whatever we have discussed with the neuron output is applicable even to weights.
So the change in proportion of weights will be proportionate to change in error, madam.
Yes. So we can say that, in other words, when any weights in the network changes, the error changes by a proportional amount. So we could, if we wanted, we could work out a delta for every weight. So now we worked out a delta for every neuron. So we can work out a delta for every weight, and that would be even more perfect. So we would know just how to tweak the weight to how to reduce the error. Now you know that in order to reduce the error, how much we should change the neuron output. Similarly, in order to reduce the error, how much we should change the weight, we will know, we will tweak it. So are you getting the hands here, like how it is, like how we are going to, the overall aim is to reduce the error by changing the weights. So did you get it now, how we can see the error will be reduced by changing the weights? So we are coming close to that. So just by adding a small number whose sign is opposite to that of the delta, so we know that we need to choose the value of this one opposite to the sign of delta to reduce the error. So both should be in the opposite sign to reduce the error. So for this weights, we need to choose a number opposite to the value of the opposite to the sign of the delta number, and we need to choose some number so that our error will come down. So this is how we will be going on it. So this is how we will find out the deltas using back propagation. We can find them first by finding the delta for every neuron's output. So we can see below, we will see in the future, like how by finding the neuron's delta and its output, we can find the weight deltas. So back propagation, it is all about finding deltas. So deltas for these weights. So first we will find the deltas for the neuron output, and then we will find the deltas for the weight. So first we will find the output changes. Using that, we will find out the delta. And with that one, we will find out the deltas for these weights. So the beauty of back propagation algorithm is that it can find these spikes very incredibly efficient way. Is it clear?
So the delta changes for both the output as well as weights. Is a different deltas for a output as well as weight. It's not the same thing.
Of course, it is not the same. So because if you could look at it, any questions?
Nothing.
No. So if you look at it now, that is why we had two key observations. So the first observation which we had is that we are looking at the neurons output. For every neuron output, there is a proportional number. With that number, we see there is a change in the network error. So so only we have two observations. The second observation tells that weight is also proportionally changing with the change in error. So the change in weight is also related to the change in error. So every neuron will have a delta and every weight will have a delta.
Okay.
Is it clear?
Yes, ma'am.
We will understand this. Now we will go on calculate the delta for the weights, delta for the neurons and the delta for the weights. Then you will understand how are we going to update these weights and all those things we will do in detail. So far what we have done is that we have got two observations. This concept is very important. You need to understand this concept very clearly. So we need to understand that the output of the neuron changes proportionally to the change in the error, and they are related with a number, and that number is called as the delta number. So change in output into neurons delta is nothing but the change in network's error. So, and we saw how it is changing, and we can change it by either changing at the output or by changing one of the inputs, we can bring out the change in error. And we saw that to reduce the error, the sign of the change in output must be opposite to that of the delta. If they are same in number, same in the sign, then the error will increase. But they have to be in the opposite sign for that error can be reduced. This is another thing. And the second observation is that the change in the weights network is proportional to the change in the network's error. We saw that one. So whatever discussion we have done it with the neurons output is applicable to the change in weights also. So these are the two observations which we are.
If this is applies for both the both the
Hmm.
input and output stage, we can do this for weights also, ma'am, or it's only for input level?
No, in weights you don't have input and output. No. So when you look at neurons output, like how we are bringing the whole point of saying that one is how are you going to bring out a change in the output? The change in the output is brought out by either by changing the input or by changing a number in the output, by adding a number in the output. But with weights, how could you tell that?
Weights will be invariably at the input level only, no, madam?
It is not at the input or the output. Every stage you have here, if you look at here, so every edge has a weight. The whole network has a weight. Even these inputs are connected to the weights here.
Okay.
Even before the neurons get started, the inputs are connected with the weights. And here in the output also, like output layer neuron also, the weights are connected. The weights are present in the complete neural network. It is present in the every layer.
Got it.
So that is what you need to understand here. Neuron output is different from weight. So don't get confused. That is a different thing. This is a different thing.
Sure. Got it.
Okay.
Ma'am, in the last description, you did not tell about M, ma'am.
Which one, sir?
You did not use the letter M in the final conclusion.
Here, this is a second observation. M is a change in the output.
Okay,
That is
that's
just to
a
denote
short form of change in output. Okay. Got it.
Instead of writing change in output, I am writing it as M.
Okay, got it.
Okay. So now let's consider a tiny neural network and then bring our discussion with that one. So let us consider a simple neural network like this. It has two features, X and Y, two input features. It has got four neurons, A, B, C, D, or four neurons. And it has two predictions, P1 and P2. So these predictions are likelihood and they are not probabilities. They are just likelihood. So for every sample, you have got two features. You are feeding that two features as a input to this small neural network. So this neural network, you can consider it as to be classifying 2D points into two categories, class 1 and class 2. A simple perceptron would do this work, but for explaining the general principles of this one, we need a small neural network. So consider this small neural network. The job of the small neural network is to classify a 2D set of points into class 1 and class 2. So every sample either will belong to class 1 or class 2. If it is class 1, we will get this one as a high number. If it is class 2, we will get this one as a high number. So let us consider that for now, we are going to label each weights. How are we going to label each weights? Is like this. So let us, for time being, we will understand this X and Y are just inputs. They are not neurons, but for weighing purpose, we will consider the starting number of this one and the ending neuron. So it is starting from X and it is ending in A, this weight. So we can name this as XA, this as XB, this as AC, this is AD. This is starting from neuron A and ending in neuron D. So this is AD. So we have got four weights like this. So similarly for the prediction 2 also, we can name four weights. So this is YA, this is BC, this one is YB, this one is BD. We just pretend that X and Y are neurons when it is coming to the naming these weights. So if you look at it, this is a very tiny deep learning network with two layers. So what are these layers? So this is a input layer. This is layer 1. You can call this as hidden layer. This is layer 2. This is output layer. And this one is outputs. So if you look at it, the input layer does not do any computing. So it is not usually included in the input layer. Though we say it is an input layer, we call this is a two-layer network. This is a two-layer network. We are not including this one in the layer count. We are having only output layer and the hidden layer. We are having only these two layers. Input is not counted in the layer. If you look at it, this two layers is not a terribly deep network because it has only two neurons per layer. It has only two neurons per layer and it has only two layers. So it is not a very deep network. It does not include a lot of computational power. But we usually work with systems.
some doubt, madam. Generally, when it comes from X and Y, it usually be a single output, no, madam. It will not be branching to the nodes, no. Generally,
No, that is what. But we are pretending that they are like neurons. So it
okay,
is branching. It is for A will receive X and Y. B will also receive X and Y.
okay. We're presuming it to
A
be a
is
neuron.
receiving both the features. B is also receiving both the features.
Okay.
X and Y are features. So yeah, where we are. We usually consider systems with more layers and more neurons on each layer, determining how many layers determining how many neurons every layer should present and how many layers should be actually there. All these things are all experimental science, and it is an art for deciding how many layers should be present, how many neurons should be present in each layer. It is an art. So of getting all those numbers that we will, while developing architectures, by developing more architectures, we will learn on the fly. So if you look at input, the input consists of the grouping of these features. So it is a conceptual grouping of these inputs X and Y. They do not contain any neurons. If you look at it, there is no neurons present in the input layer. So this is just a piece of memory for holding these input features. So they are not usually counted. Though we call it as an input layer, they are not included in the layer count. So this should be understood. And the second thing is called as the hidden layer. So why do we call hidden layer? If somebody sees the network from the input side or from the output side, this is usually hidden. This is usually hidden from the input and the output side. If you look at from the input layer is visible. If you look at from the output layer is visible. This layer is not visible. This is hidden. So only it is called as hidden layer. Next, we have the output layer, the set of neurons which will produce our output. So here C and D are the output layer neuron. The output which comes from C is P1. The output which comes from D is P2. So these are the set of neurons which provides their output. If you look at the input layer, there is no neuron, but output layer has neurons. So that is the difference between input layer and the output layer. Is it clear?
Yes, ma'am.
So we will go to one more step and then explain it a little bit further. So in the previous discussion, we saw every neuron has an output and also a number associated with it, A delta. So I can write this has an output, A delta, B output, B delta, C output, C delta, D output, D delta. So every every neuron has an output associated with it, and every neuron also has a delta value associated with it. So what happens when the neuron output changes? It changes the error to change. It causes the error to change. So we have labeled it like this. So now let us understand how the output will be affecting the change in error. So if you look at it, so we have our starting output A naught. So this is from here to here, you have the value A naught. So now by some change, you are changing the input or you are changing your weight. Because of that, there is a change in the output. So this change in output is shown by this arrow mark. So previously your output was still here. Now because of some change, the output has changed like this. So AM is the change in output. So the new output is A naught plus AM. So the starting output plus change in output is your new output A naught plus AM. So this is the output of neuron A. So this is the output of neuron A. So now what we learned, the change in output into delta will give you the change in error. So this delta is an amplifier. If you look at it, it's a wedge shaped, this is a wedge shaped diagram. So it is showing that it is amplifying it. Whatever is present here, it is amplifying the change. So the change in output is amplified by A delta. That will give you the change in error. So how I can write it? AM into A delta is equal to EM. AM into A delta is equal to EM. We saw that every neuron has a delta. From here we saw every neuron has a delta value. So this AM is getting multiplied by A delta to get the EM value, which is the change in the error. So the starting error before this change has happened, the starting error was E. So now there is a change in error. So the total new error is starting error plus change in error. So that is your new error. So the new error of the network is E plus EM. Is it clear? We have drawn it only for one neuron, but this will happen for across every neuron. Is it clear? So
Yes, yes, ma'am.
So initially we have defined an output for every neuron. Let's consider one neuron A. For this neuron, A naught is the starting output and it has a value called A delta. Every neuron has an associated value called delta. So we have defined the value delta. So this is the starting output of the neuron. For the starting output of the neuron, there is some change which is happening because you changed input or you have changed some weight. Because of some change, there is a change in the output. So the new output is A naught plus AM. A naught we have it already. AM is the change in the output. So now we have the A delta value. So what this A delta will act like an amplifier. So this will amplify the change in the neuron. So here the change in neuron is positive. If you look at it, it is a positive sign. The A delta value is also a positive sign. So both the signs are positive. The error will increase. Initially, the error was only here. So now the error will increase because both the values are positive. The error will increase. So this is increasing from the starting value of the error. So this is the starting value of the error, which is network error. Now the error is increased because of this. So the change in error is a positive thing. So the whole error will increase. The whole error is increased by E plus EM. Is it clear?
Yes, ma'am.
Yep. So we need to understand that we need to keep in mind that this delta value is related to the change in the neuron output to the change in the error. It is not a relative or a percentage change, but it is an actual amount. So let us assume that if the output of A goes from 3 to 5, that means the change in output is The change in error is A delta into 2. The change in output into delta value is the change in error. So this is one thing. Let us imagine if the output of A goes from 3000 to 3002. Now the change in output is 2. The change in error is also A delta into 2. So if you look at it, in both the cases, the change in error is only A delta into 2, A delta into 2. Whatever, regardless of from where to where the output changes, it is looking only at the actual amount. So the same number. So now we are finally ready to look into this back propagation algorithm. Today we will just see the, we will start with this and we will see detailedly in the next class. So now the delta number is clear to you?
Yes, ma'am.
Yeah. So we will look at the, as a first step, we will look at how to calculate the deltas for the neurons output. So we know that we are going to calculate it through back propagation. So what is back propagation? Finding the delta values for each neuron is back propagation. So how are we going to find that? We will find the gradient of error at the end of network. And then after finding the gradient, we need to propagate those gradients back to the start. So that only it has got the name back propagation. So what we are going to do is that we are going to begin at the end of the output layer. So what we are going to do, we are essentially going to look at the output of the output layer neurons. Output layer neurons are C and D in RRT. So this is are going to give the likelihood. The C and D is going to give the likelihoods of the input, whether they belong to class 1 or class 2. If it is going to be a perfect system, then we can say if the neural network is a perfect perfect system, then we can say P1 is equal to, for class 1, P1 is equal to 0.1, P2 is equal to 0.2, sorry, 0.0. So if the system is less certain, then it can give P1 is equal to 0.8, P2 is equal to 0.1. So still it belongs to class 1. It is much more likely if the sample belongs to class 1 and P2 is 0.1. Note that this is not probability. When we are not adding it to 1, this is only likelihood. So it should not, it is not like if we add, it has to come to the number 1. So for this kind of a system, we would like to come up with a single number which represents the error. So what we will do, we will calculate the likelihood and then compare it with the system label to find out a error. So the easiest way to do this one is through one-hot encoding. One-hot encoding, what we will do? In one-hot encoding, we will put every entry as 0. And for the corresponding entry, we will put as 1. So suppose if we have two classes, class 1 and class 2. Class 1 can be written as 1, 0, and class 2 can be written as 0, 1. So these are called as labels or targets. So what we will do, and similarly our predictions P1 and P2 can be written like this in a list form. So what we are essentially doing here, we have our neural network. So this has two predictions, P1, P2. So we will compare it with the label. Using an error formula. This error formula will give the error. So to find the error from a specific sample, what we are doing, we are supplying the sample features to the network. So we will supply the sample features to the network for a single sample. We want to find the error. We'll supply the sample features to the network. It will get some predictions, and we already have the label for this sample. So we will compare these things using an error formula, and we will get an error. This error will tell us, suppose if this error is 0, then we will know this is a perfectly matching. If there is a bigger mismatch, then the error will be bigger. So if the prediction list is identical to the label list, the error is 0. If the two lists are very close, so for example, if you say this one is the prediction label is 0.9, 0.1, and the label is 1, 0, they are very close to each other. Then they are very close, then we will come up with a number something greater than 0. Suppose if the prediction label is 1, 0, it's a complete mismatch. This one is 0, 1, then the error will be maximum. So there are a lot of error formulas for calculating errors from the libraries. There are, if you are using if you are building a network to classify inputs into several categories, there is one type of error. So if there is another type of error formula for predicting the next value in the sequence, there is another type of formula if you are trying to match the output of some other network. So there are different kinds of error formulas. So based on what you wanted to do, there are different kinds of error formulas. So you can use those error formulas here to calculate the error from the predictions and the label. So this is the concept which we are going to do. So but the common property the error formula will share is that we will compare the classifier output to the label. So the predictions will be compared with the label. If it is a perfect match, we will get 0. If it is incorrect, then we will get an increasingly larger error. So that is the common property among all the error formulas, whatever error formula used. So this is the property which if the comparison, if the mismatch is there, then we will get a number greater than 0. If there is perfectly matching, then we will get a 0 as a error. So, and another point to remember here is that, so each type of error formula, we will be provided with a gradient. So what this gradient will do? This gradient will tell us how the error will change. So in a simplest case, the gradient will tell us whether we would like the error. By seeing the gradient, we will come to know whether we need to increase the output or decrease the output, whether we need to increase our weight or decrease the weight. So we will come to the conclusion by seeing the error gradients. So this is what is for today. From next class onwards, we will see deeper into how to calculate this delta and all other things. So in today's class, what we did is that we started off with two observations. The first observation told us how the change in the network output is related to the change in the error. That is through a number called delta. And we saw how the relationship between the delta and how they are connected and all these things. Then we also came up with the second observation that the weights is also related to the network error by the same means of delta. So, and we took a small neural network to understand this one. And we explained this neural network. And we saw the relationship between the change in output to the change in error, and how it is related with this neural network. And we just started off with the calculation of deltas for the output neurons. So for that, we understood what is the backpropagation algorithm. We are starting it from the end. So first we need to find the delta value for each of these neurons. And once it is found, using the gradient of the error, we are going to propagate that gradient from the backwards to the front. So we are going to start at the output layer and then propagate to the front. So, and then we saw how are we going to calculate the error. So how we are going to calculate, the general thing to be remembered here is that we compare the prediction with the label. If the match is there, then the error is 0. If the match is not there, if it is incorrectly matching, then the error value will be high. We can use any of the error formulas from the libraries. We choose the error formulas based on the task which is at our hand. And then we use the gradient to decide how the error will change. If you want to increase the error or decrease the error, we look at the gradient and we will decide that one. So is it clear?
Yes, ma'am.
Okay. So on Good Friday and on Tamil New Year, we will not have class. We will see on 21st. And your project presentation will be on May 11th. I have already said in the group, but you have to come and present, and you have to submit your project report before that.
Sure.
Okay. Yeah.
Okay.
Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.